Okay, in this lesson, I want to cover 4 different types of counting methods. Actually, the first thing we're going to do is review the fundamental counting principle, which we covered really in the first page of this note pack, but I want to include it here and review it so that you can see how it differs from the other 3 methods that we're going to be talking about. Okay, in this particular example, a recent advertising campaign, Applebee's restaurant offered diners a special 3-course menu for $15.99. The menu included choices of 3 appetizers, 4 entrees, and 2 desserts. We have 3 different questions that we're going to answer. How many different 3-course meals can be ordered from this menu? Okay, we had 3 different choices for appetizers, 4 different choices for entree, and 2 different choices for dessert. So the quick and easy way to do this would just be to multiply those number of options. So 3 times 4 times 2 would give us 24. Now on page 1 of your notebook, I showed you how we could do, or notepad, I showed you how we could do a tree diagram, which helps you to visualize how the number of combinations here can really explode, and it can get kind of crazy if you're relying on the tree diagram. This is way easier. Okay, part B. How many of these 3-course meals have beef course as the entree? Again, we have 3 appetizers. This time we only have 1 entree and 2 dessert choices. So 3 times 1 times 2, so we would have 6 options that would include beef as the main entree. So our probability question is what is the probability that a 3-course meal has the beef entree, if all things are being equal there? Okay, so again, we're looking at 6 is partial, the number of combinations in our sample space that have beef as the main course, and 24 is the total number of combinations in our sample space. So I divide that out, we have basically a 25% chance or probability of having a meal with a beef entree. So that is the fundamental counting principle, where you list your different options and how many possibilities you have for each option, and you take the product. Okay, on our next one, the next 3 things, we really have some new notation that we're going to need to be dealing with, as well as some new concepts. So our first one is the factorial rule. The number of different arrangements of n different times when all n of them are selected is the product of decreasing positive whole numbers. This is called the factorial rule and is denoted by n exclamation point. Now, at first you're like, that was a lovely definition, but what in the heck does that mean? It's very convoluted sounding. Arrangements mean that the members are in a different order, count as a new arrangement. So we need to keep that in mind. I think the best way to do this is just do an example. How many different ways can 5 runners place in the top 5 spots of a cross-country meet? Well, let's just assume that we only have 5 runners. Then we're going to look at what is the probability of any one of these arrangements. So we have 5 runners. I want you to see that you really would kind of create 5 different spaces. So in our first place, we have 5 different possibilities. Once somebody comes in and finishes first, second place only has 4 possibilities. When somebody comes in and finishes second, third place only has 3 possibilities, and after that we only have 2 left for 4th place, and then obviously 1 for our 5th place. So when we multiply the product here, we come up with 120 different ways that this can occur. And this is just a quick, slick way of calculating that total number of possibilities. Each of these possibilities has a 1 over 120th probability of occurring if everything was being equal. And I really probably should have divided that out and given you the decimal notation for that as well. But basically, factorial, n factorial just means you take that number and multiply by all the preceding whole numbers after that. Okay, our next lesson, I kind of went too far there. Our next topic is permutations. And again, kind of a convoluted definition here. I would like you to understand the formula here and how it compares to the next thing that we're going to be doing. Permutations of items are arrangements from a larger group in which different sequences of the same items are counted separately. So arrangement means that the members in a different order count as a different group. So again, I think the best thing to do is talk about an example. In a horse race, a trifecta bet is won by correctly selecting the horses that finish first, second, and third, and you must select them in the order, the correct order, to win the trifecta bet. Okay, in the 140th running of the Kentucky Derby, they had a field of 19 horses. So we want to find the total number of permutations or possibilities for how the top 3 horses could have come in, and then find the probability of calling the winning ticket with all things being equal. So this is our notation, NPR. Now again, N is the total number of objects in our sample space. R is selected at how many at a time. So NPR. And order here really does matter, and so you could plug in this formula and calculate out. So 19 factorial, I'm going to write 19 times 18 times 17 times 16. I could continue on times 15 times 14, but I'd fill out my page. So I'm just going to end it with 16 factorial. And our denominator, n minus r, would be 19 minus 3, which is 16 factorial. That's partly why I stopped at 16 factorial, because I can see that a majority of this all eliminates. So when I pull out my calculator and multiply 19 times 18 times 17, we come up with a huge number of permutations, 5,814 different ways that the top 3 horses could come in a field of 19. So it's not very likely that you're going to win the ticket if you don't know something about the horse race. So each of these possible permutations has a 1 over 5,814 possibility of being selected. So when we calculate that out, we come up with a really, really tiny decimal. So there's not much chance that that's going to occur. So that's why you win a lot if you win that. You can do this on your graphing calculator, or any kind of a scientific calculator, but you're going to need to locate the NPR button. You need to recognize that on any of these, the factorial as well as the permutations and the combinations, you're going to need to put in n first before you access the factorial, the permutation, or the combination key on your calculator. So on your calculator, you would put in 19 first, access the permutations button, select it, and then you're going to have to tell your calculator that you want to take this 3 at a time. And then we'll find out that we have, again, the same outcome, 5,814 possible ways that can happen. Okay, moving on to combinations is very, very similar to permutations with one key difference. Combinations of items are arrangements from a larger group in which different sequences of the same items are counted as being the same. So we basically need to remove all that duplication in combinations by dividing by r factorial in addition to what we did with our permutations. So again, I think an example is going to help us make sense of this. In California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 through 39, and the same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in any order, so order really does not matter. Okay, so how many different lottery tickets are possible? We're going to find the probability of the winning jackpot when 1 ticket is purchased. So I'm just going to talk about how you do this on the calculator. You're going to need to locate your combinations key, which would be NCR. What you would enter first is you need to put in 39. Then click on that NCR button, and it's going to prompt you to say how many at a time in the R. So you're going to put in 5. So basically we come up with quite a few combinations, over 500,000 different combinations. Any one of those combinations would have 2 1/millionths probability of winning. So that's why the jackpots are so valuable. Okay, another example, going back to our trifecta, how you can see how the trifecta is different from this scenario. An alternative to betting on the trifecta in the horse race example, bettors can choose to place a bet where they select the top 3 horses, but this time in any order. Because it can be in any order, you have a much better chance of possibly winning. We want to find total number of combinations. So here again, you're going to use that same button, but before you can use that on your calculator, you need to enter 19 first, because that's the total number of objects in our space. So 19, our combinations key, and it's going to be prompting you for what is R, how many at a time, 3 at a time. Now we come up with only 969 combinations because we've removed all that duplication where we have the same horses but in different orders. Order in this case does not matter. So we can see when we divide that out, 1 divided by 969 comes up with a much better probability. 1,000th still isn't great, but it's better than 2 millionths. Okay, so for the rest of this activity, I have some practice where you are looking at some problems that all sound kind of similar. They have the same data set. We are answering all 6 of these questions. 2 students are selected from a class of 18 female and 12 male students. I wanted to look at how this really has the same basic starting point, but the questions are all different. Here we're looking at finding probability without replacement, looking for 2 females, 2 males, or 1 male and 1 female. When, remember, we had this could happen 2 different ways. We've done this kind of scenario before, but I wanted you to see that in comparison to part D, E, and F. The professor in this class above would like to organize a committee to help critique a new textbook. These are combinations because the order does not matter in a committee. It doesn't matter who is selected first, second, third, or fourth. The committee is the committee. So we're going to be using our combinations key to meet each of these features. So you can look that over, give that a shot, and check your work here.